All right, 4-3, we're looking at the product of complex numbers. Woo, this is amazing. All right, so it starts off by talking about vector representation of complex numbers. A vector is anything expressed as a magnitude or direction. So let's see what it says. A quantity that is expressed as a direction, which is the argument, and a magnitude, the modulus. Here's some fun words. Let's make them easier for ourselves. Polar coordinates of both real and complex numbers. Because it has a direction, that's your theta, and it has a magnitude, right? That's your r, your distance from the origin. There is r. So it tells us this Argand diagram, a vector representation of a complex number on the complex number plane. Boy, that's a lot. That's just a lot to say. Here's a coordinate point in the form of a plus bi. Right, so we'll say that's rectangular. Or you could think of this in terms of some distance from the origin and some angle, right? So the angle tells us the direction. The angle tells us the direction, and r tells us the distance. So that is the polar, right? So these are vectors. Vectors can come in different shapes and sizes. Do not mix this up with your physics vectors, even though they're all the same, all the exact same. But here we're just strictly dealing in terms of complex numbers. We're looking at complex numbers in different ways, and I think it's a beautiful, fun set of patterns to kind of take a look at. All right, so magnitude and direction. Magnitude is the distance of z from z being the number, right, the coordinate point. The distance of that coordinate point from 0, or let's call it the origin. That feels a lot better. You could also think of this as absolute value of z, the modulus. Right, so the absolute value of z is the square root of a squared plus b squared, which is nothing more than r, right? The absolute value of z is r. So if you're ever asked to find an absolute value, what is r? All right, absolute value is nothing more than r. I don't know whatever else to say about that page. All right, roll it over. Here we go. The product of complex numbers. Now, this is where it gets cool. So the product of two complex numbers in polar form. So we're going to multiply the r value. I don't know why I'm looking at this diagram. Just tell us, multiply the moduli. That's your r's. And sum the arguments. That's the theta. All right, so it says if z1 is equal to r1 cis theta 1, and z2 is r2 cis theta 2, then z1 times z2 is equal to r1 times r2 cis theta 1 plus theta 2. And that's the part. That's the part we want to take a look at. I think it might be really good to look at this in terms of like rectangular and polar. Let's see what's polar. Oh yeah, it's gonna get us there. Okay, all right, sweet. So let's just follow the form. Express each product in polar form. All right, 2 times 3 is 6, and 50 plus 20 is 70, and we're done. Okay, not too terribly difficult. You make fun of me for that. 6, there we go, it's better. Okay. All right, multiply the moduli, add the theta. All right, so here, 3 times 5 gives us 15, CIS. Okay, so pi over 4 plus 2 pi over 3, 12? Something over 12 plus something over 12. I got to go times 3 there, so we'll end up with 3 pi over 12, and I got to go times 4 there plus 8 pi over 12, and then we count, add our numerators. 3 pi's over 12 plus 8 pi's over 12 is a grand total of 11 pi's over 12. All right, we're in good shape. Really good shape. So let's try another one. R cis theta times R cis theta. That would be R squared CIS 2 theta. Okay, all right. No, not too terribly difficult there. Now, uh, it says for the following complex numbers, we want to find Z1 and Z2 in rectangular form, as well as a quotient. Ooh, it wants quotient too. Ooh. All right. And then we need to go to convert it into polar form, and we're going to multiply them as well as the quotient. So we're going to multiply and divide in rectangular and polar form. All right. So here we're in rectangular. Let's switch this to polar form. All right. So going into polar form, we have 3 plus 3i. So knowing that 3 plus 3i is going to be somewhere up here, right? And I know that the tangent inverse of 1 or 3 over 3 is just 45. So I got the angle down. The distance, though, we got to go figure that out. So r squared is equal to 3 squared plus 3 squared. Well, there's two of those. So r squared is equal to 9 plus 9. R squared is equal to 18. So r must be equal to 3 roots of 2. All right. So we know that z1 is equal to 3 root 2 CIS of 45. All right. And now we have this 1 plus I root 3. Here we go. R squared is 1 squared plus root 3 squared. So r squared is equal to 1 plus 3. R squared is equal to 4. R is equal to 2. And now we got to go figure out tangent inverse of root 3 over 1. I can do this without using a calculator. So tangent theta is equal to root 3 over 1, which is the square root of 3 over 2 divided by 1 at 1/2. And it's all positive, right? I know I'm in the first quadrant here. A positive 1 and a positive root 3, positive 1. It puts me in the first quadrant. So in the first quadrant, we have sine divided by cosine. So the sine, or my y value is root 3, my x value is 1/2. That, my friends, is up here at 60 degrees. So we get Z2, R is 2, CIS of 60. This is working out really well. Okay, so now we just have to multiply, divide in rectangular and polar. So we're going to start with multiplying in rectangular, meaning 3 plus 3i times 1 plus I root 3. Now, how do you think we're going to multiply that? Well, you're right. 3 times 1 is 3. 3 times I root 3 is a positive 3 root 3. Oh, no, I don't want the I there. 3i root 3 plus 3i times 1, which is a positive 3i. Then 3i times root I root, good gravy. That is a positive 3i root 3. That's an I squared, Dave. You're right. You're right. And I squared is -1, so that turns that into a minus. So combining our like terms, since this is a minus, we have 3 minus 3 root 3 plus 3 plus 3 root 3 times I. That's gross. I don't like it, not one bit. I don't like it, not one bit. So that's as good as we can get. All right, let's try dividing these things. 3 plus 3i divided by 1 plus yo I root 3. And we multiply the top and the bottom by the conjugate of the denominator, right? The conjugate of the denominator. So we get 1 minus I root 3 and 1 minus I root 3. And when we multiply across the top, we have to FOIL, so 3 minus 3I root 3. And then we get plus 3I minus 3I squared root 3 all over. And conjugates in the denominator turns out to be really friendly. It's just a squared plus b squared. So 1 plus 3. Right? Root 3 squared is just 3. That's friendly. The rest of it's kind of gross. So we end up with I squared is -1, so it's a plus. So we get 3 plus 3 root 3. That's the real part. And now the imaginary part is that we have a positive 3, a negative 3 root 3 times I. And now I know you guys are like freaking out. Oh my gosh, I'll never be able to. Don't worry. I'm not going to put anything that hectic on a quiz or a test. And why they want us to do this, I don't know why we want to do this in rectangular form, but that's what they asked us to do. So there we are. And now let's multiply and divide in polar form. All right, so we want to multiply. We have 3 root 2 CIS 45 times 2 CIS 60. And on the marks I go. 3 times 2 is 6, so we get 6 root 2 CIS 45 plus it's 105. That. Now, if we're going to divide, right, division matters. The order matters with division, right? So since multiplication, we multiply. We're multiplying, and then we add the argument. We multiply the radius, add the argument. So division, we would divide the radius and subtract the argument, right? So we get 3 root 2 CIS 45 divided by 2 CIS 60. It's going to be equal to 3 root 2 over 2 CIS 45 minus 60 is negative 15. I don't think we leave it as negative 15, right? It has to be between 0 and 360, so what, 345? We'll leave it negative 15 for now. So we get 3 root 2 over 2 CIS 345. I think it would be cool to show that these are equivalent statements. I'm not going to do that here on this video, but it would be really cool to show that these two are indeed equivalent statements. Probably Desmos will have something fun for us. We'll do that in class one day. If you want. I don't know. Your call. That's it.